Professor Makoto Fujita, Distinguished University Professor at the University of Tokyo, NUS Deputy President of Research and Technology, Professor Liu Bin, distinguished guests, ladies and gentlemen, good afternoon and welcome to the Lee Kuan Yew Distinguished Visitors Program. I am Min Hui, a fourth-year student from the Faculty of Science, and I am the Master of Ceremonies of this event. The Lee Kuan Yew Distinguished Visitors Program invites internationally eminent and outstanding academics and scholars to Singapore as Lee Kuan Yew Distinguished Visitors to make high-level contributions to NUS, NTU, and to Singapore in general. I will now invite Professor Liu Xiaogang, Distinguished Professor of the Department of Chemistry at NUS, for the introduction.
Good afternoon. Thank you all for being here today. I think everyone knows me. I'm Xiaogang Liu from the Department of Chemistry, Faculty of Science. I'm absolutely delighted to welcome Dr. Makoto Fujita, who is the recipient of this year's Lee Kuan Yew Distinguished Visitors Program. So before I continue, I would like to thank Jun Chen and Yuhan Loki for their hard work in coordinating all logistics for this visit, and also the Lee Kuan Yew Endowment Fund for their general support in making this event possible. So let me start by briefly sharing what this program represents. The Distinguished Visitors Program brings to Singapore exceptional global leaders, people whose vision, creativity, and impact reflect the innovative spirit of our founding Prime Minister, Mr. Lee Kuan Yew. These visitors are chosen not only for their scientific achievements, but also for the way they shape new fields and inspire future generations. Dr. Fujita received his PhD from the Tokyo Institute of Technology in 1987, and then hold positions at Chiba University, the Institute for Molecular Science in Okazaki, and also Nagoya University. In 2002, he joined the University of Tokyo as a full professor, and in recognition of his extraordinary contributions, he was awarded the title of University Distinguished Professor in 2019. Many of you know him as one of the pioneers of modern supermolecular chemistry. He introduced metal-directed self-assembly, a concept that completely transformed how we think about building complex molecular structures using a beautiful, simple idea. The predictable geometry of a metal-ligand coordination. He showed that molecules can spontaneously organize into rings, catenins, cages, and three-dimensional polyhedral. His landmark 1990 paper in JAX describing palladium cornered self-assembly square is now seen as a foundational breakthrough. From that single achievement, an entire generation of molecular designers has drawn inspiration, I think also including the development of metal-organic frameworks. So since then, Dr. Fujita has continued to push the boundaries of the field, developing increasingly sophisticated systems, giant coordination cages, functional molecular containers, and also supermolecular hosts capable of binding proteins and reactive intermediates. And among his many contributions, I think one stands out as truly transformative, the crystalline sponging method. This breakthrough allows scientists to determine the structure of molecules that cannot be crystallized, solving a long-standing challenge in synthetic and pharmaceutical chemistry. Today, this method is widely used around the world in both academia and industry. So over his remarkable career, Dr. Fujita has deepened our understanding of molecular recognition, self-organization, catalysis, porous materials, and then the design of functional molecular systems. His influence extends across chemistry, material science, biology, and beyond. It is no surprise that his seminal work has been recognized with some of the highest honors in science, the Kazari Prize, the Wolf Prize in Chemistry, the Imperial Prize and the Japan Academy Prize, and the Arthur Baylor Latour Health Prize, and also the Asahi Prize among many others. We are truly fortunate to have him with us today, not only as a world-leading scientist, but as someone whose idea continue to shape the future of chemical science. Please join me in welcoming Professor Makoto Fujita for his lecture, Molecular Confinement Effects in Coordination Cages. Please welcome.
Okay, thank you, Professor Xiaogang. So, first of all, I'd like to thank Professor Liu Bing for inviting me to Singapore with such prestigious opportunities. So, also, thank you very much, Xiaogang, for arranging everything, so nominating me and arranging everything. Okay, so in this lecture, I want to disclose most of the work which we have been working, we have worked for during the last decades. So, and my lecture will be consist of the two parts. Today is the first part. Okay, the part two will be given on Thursday at NTU. Yeah, of course. Yeah, if you are interested in, you are also invited. But today, so I would like to focus on the molecular confinement effects in coordination cases. So let me start. So what the confinement effects? This is just the inspiration from the physical term, so quantum confinement effects. When electrons are confined within the nanostructures, then new physical properties will emerge. So the physical people say that this is the quantum confinement effects. So let's translate this term into chemical words. So when molecules are confined within the nanospace, then the new chemical properties will emerge. This is the molecular confinement effect, which we want to define and emphasize. Maybe the Julius Riebeck's the tennis ball assembly is one of the landmark pioneering work on molecular confinement in a self-assembled cage or capsule host molecules. Okay, so in our studies, we have been using the metal ligand weak coordinations. So when the metal is added to the solution of very simple bridging organic molecules, then all the species try to find the right pathway leading to the most stable structure. So in this case, this spherical framework is self-assembled in a quantitative field. So from this animation, you can understand the power and the principle of self-assembly based on coordination chemistry. So our long study was kicked off in 1990 by showing the self-assembly of a palladium-cornered square molecule from a 90-degree coordination block and a linear organic molecules. So even back 80s, we can find some historical milestones in these works, such as Sauvage catenane or double helical complexes by Jean-Marie Ren and Ed Constable, and the cage-like cluster by Darfrans. However, these earlier examples didn't show any particular functions. So in our self-assembly, we created not only the framework, but also a cavity, which is an excellent platform for further developing the new functions, properties, and the reaction therein. So that's the reason why we can be working in this area for many, many years. Namely, our chemistry can be featured as the self-assembly construction of chemically defined cavities. So the chemical cavities was, so the construction was further ascribed to the discovery of granulism in 1960s. But around 70s or 80s, this field became almost saturated because of the synthetic limitations. So synthesizing the much larger or more complicated, more functional host molecules becomes harder and harder. So there are limitations in covalent synthesis. However, the self-assembly removed such a synthetic limitation. Only by mixing the metals and ligands, we can create two-dimensional or even three-dimensional cavities in which we can confine their molecules. And in mid-90s, we and others created three-dimensional host molecules by self-assembly. And all of us enjoyed their creation of new properties, new functions, reactions by showing the molecular confinement effects in a cage. So in recent years, our cage is getting larger and larger. So this is the main story of our chemistry. But back to 90s, from the square molecules, we could make there are a few other directions, few other branches in this project, in this work. So before going to the main story, I just want to quickly show you the one very important branch of our chemistry. So in 1994, we reported the self-assembly of linked ring molecules or catenane. Okay, so nowadays catenane is not very special molecules, but back to 80s or 90s, it's really so curious molecules. So even back to 18th century, this is the molecule of just imagination. So everybody wondered what happens if the molecular rings are connected. So they are not linked, but topologically linked. So they wondered how we can synthesize and how the molecule should show properties. Okay? Then so two giants, Jean-Pierre Sauvage and Fraser Stoddart, developed highly efficient synthesis of catenane in 80s. So our catenane synthesis is, of course, 10 years behind their creative works, but our catenane synthesis is quite different, distinctly different from the previous covalent synthesis of catenanes, in which the catenane is formed from two preformed molecular rings by the slippage. So we can say the two molecular rings can slide into a catenane via the topologically forbidden process. So in terms of topology, so mathematicians say that the coffee mug cup and the donuts are equivalent because they can be converted to each other without breaking its structure. Only by deforming, so they can convert to each other. So mathematicians say they are equivalent. A bit curious person, okay? But they never accept this transformation because this is topologically forbidden. However, the reversible coordination bond made it possible to realize this transformation. So at the beginning, we are very happy to synthesize the catenane, but time to time we realize the scientific significance of this transformation is just the the discovery that the topologically forbidden process became allowed. And based on this principle, we have synthesized many interlocking compounds. Okay? So some are catenated or are three-dimensionally interlocked. And some are designed, and some are obtained by chance. And quite recently, we are using peptide fragments as an organic ligand. And we realized their peptide shows their entangling nature. So they want to entangle to each other. And because so the molecular system is completely free from the topological restrictions, we obtained highly entangled metal peptide architectures. Here is one example. I do not show the chemical structure, but just this so strand is a peptide. So amino acid, amino acid, amino acid, having the two coordination sites at their both end. What we wanted to examine is, so our idea was as follows. So just a short fragment adapt a random orientation, random conformations. They do not show adapt any particular conformation, okay? But when it's linked with metal, then a peptide metal, the long chain would show their folding properties. So like the alpha helix or beta sheet structures. Then we expected the spontaneous, the self-assembly and the folding in concert. It was our original idea. And we examined many peptide fragments, and we very often encountered the highly entangled structure. Yes, self-assembly and folding occurred in concert. And in addition, we observed the very facile entanglement of peptide strands because topological restriction is removed. Here, you can see the identical 6 metal peptide rings. They are highly entangled, leading to the 24 crossing catenane structure. We discussed with a mathematician, and they say this is classified as a cubic link. So let's place 6 rings at the 6 faces of a cube. And then you can make the double twisting on every edge of the cube. Then you can get their 24 crossing structure. This is a cubic link. So it has their almost closed shell structure with a huge interior volume. So we are now developing the chemistry inside the capsid-like peptide structure. So you may not believe that we actually designed this cubic structure. Okay, it's not a by chance structure we designed because we had already synthesized the M12L12 tetrahedral link with T symmetry. So in this case, its shape is a tetrahedron. So again, you can place 4 rings on all the faces, and by making the double twisting on every edge, then you can get the 12 crossing tetrahedral link. So tetrahedron is one of the 5 Archimedean solids, the Platonic solids, regular polygons. And the 3 of them, okay, so tetrahedron, the cube, and the dodecahedron, so these, they are just brothers. So they are trivalent regular polygons. That means 3 edges meet at every vertex. Okay? They are just brothers. Difference is only the one angle, only the angle between the edges. Only one difference in the structural parameters. So we believed by modifying their peptide sequence, by slightly changing the steric demand of the substituents of the peptide strands, then we believed that tetrahedral ring should jump to their cubic link. And it realized. Yeah, of course, we did considerable trial and error, we targeted this cubic link structure. So having the cubic link in hand, then our next challenge is to synthesize the dodecahedral link. So from scratch, this is a really crazy target. Nobody can design, and nobody would like to try to synthesize such a highly complicated structure. But for us, so it's just the there is only one difference in structural parameters. So we believed we could jump to the dodecahedral link. Then we further continued the trial and error to modify the peptide sequence and steric demands on the substituents. And finally, so early in this year, we got M60, L60 dodecahedron. So you can find the pentagons, metal peptide, pentagons. And the 12 identical rings are crossing. So with 2 crossing on every edge. Then forming the 60 crossing dodecahedral ring. So it contains 300 amino acid residues. The molecular weight is over 50 kilodalton. This is almost equivalent to a protein or a large capsid, virus capsid. Again, it has a well-closed shell structure with a distinct pores through which small molecule can address inside the capsid. So, and also we know the chemical structure. So this is an X-ray structure. That means we can functionalize at any position. So at the interior of the sphere and also the surface of the sphere. So now we are functionalizing this metal peptide cages. Okay, again, you can understand the power of self-assembly. So now our chemical synthesis is very close to the nature's synthesis using peptides. Okay, let me back to the overview. So as I mentioned, our main story is here. So in mid-90s, we succeeded in the self-assembly of three-dimensional cages. Nowadays, in the literatures, you can find many cages and capsules which are constructed by self-assembly. And the design principle have been established that you can easily design, synthesize. But at that time, there were no example and no synthetic strategies principle existed. So we first designed this cage not based on logic, but by serendipity. So we wondered what happens if a triangle is combined with a 90-degree. So can you imagine? Or just a 3 triangular panels can be combined with a 90-degree block, then what structure will form? So it was a bit hard question even for us. Then I could not predict by writing the chemical structure on the paper. But finally, I played with a chemical toy, just a ball and stick model. Then after a couple of minutes, I realized that these components should assemble into this symmetry. And this chemical toy prediction really worked. So only by mixing the 90-degree palladium block and the triazine core triangular ligand, we observed the quantitative self-assembly of M6L4 cage. So At that time, the cavity was the largest among all the synthetic host molecules. And we had a big bonus. So thanks to the cationic nature of the palladium centers, the cage was highly soluble in water. And in water, they are hydrophobic and also the electron deficient and the slightly polar triazine ligand offered highly efficient guest binding pocket. So due to their the hydrophobic effects and also their electrostatic interactions, and so on. And the guest molecules were strongly bound to the cavities in aqueous solution. And the cavity was so large that it could accommodate multiple number of small molecules. This is very important. We can confine the 2 or 3 guest molecules in the cavities. Then we can create new properties by the aggregation of molecules, or we can develop new chemical reactions by associating the multiple number of molecules in the cage. So it has been already more than 30 years since the first report on the M6L4 cage. But so during the last 3 decades, we published many papers discussing the new functions, properties, and reactions. So the cage is still one of the center players in our laboratory. So namely, our cage has been showing the remarkable molecular confinement effects. Yeah, actually, so this ligand is really miracle ligand, offering the very efficient guest binding pocket. Okay, so in these examples, here we developed the method for the pairwise selective recognition of 2 different molecules. The first molecule can be planar, so stacking on the triazine ligand, and the remaining void space is filled with a bit smaller and round-shaped molecule. Then always a pair of these 2 different molecules are efficiently confined in a pairwise selective fashion. So this observation is very important to design new chemical reactions, because the most chemical reactions are bimolecular events between the 2 different molecules. So we could accommodate the peptide oligomers in a sequence selective fashion. So otherwise unstable metal complexes can be confined, or very labile unsaturated metal species can be generated in situ in the cage and could be observed by X-ray structure analysis. They are so stable thanks to their confinement effect. So let me discuss about their chemical reactions in the cage. Actually, we developed many reactions, but so in particular, the cage is quite efficient to promote the multiple centered reaction, such as Diels-Alder reaction or 2+2 photo additions. So for the multiple centered reactions, then the entropy barrier is very high. So in most cases, the reactions are prevented from the high entropy barrier of the reactions. Okay? But in our case, the 2 substrates are well pre-organized. So the entropy cost has been already paid. You don't need to pay their entropy cost. Okay? Then the entropy barrier significantly reduces. Then even the stable aromatic compounds, naphthalene, triphenylene, or anthracene, terminal benzene ring, could participate in the Diels-Alder reaction with a quite common dienophile. We never activated the substrate, just confined, and we made the close proximity of the two substrates. Then the entropy cost barrier significantly reduces, and even the stable aromatic molecules can undergo these other reactions. So for anthracene, not the middle ring, but the terminal benzene ring was the reaction center. Because in the pre-organization, before the reaction, so the reaction center of the dienophile could address to only the terminal benzene ring. So that's the reason why we observed quite unusual Diels-Harder reaction with anthracene. Similar pairs were irradiated. Then we observed highly efficient 2+2 cross addition from two different olefins. Honestly, the 2+2 photoreaction is not a very useful reactions from synthetic viewpoints. So in most cases, yields are not very high, except for a few exceptions. So one reason is, though even if one olefin is excited, it can immediately go back to the ground state before meeting its counterpart. When one olefin is photoexcited, then its counterpart is already there, already here. Then immediately the 2+2 reaction undergoes. In all cases, stereochemistries, regiochemistries are perfectly controlled. And we achieved quite unusual 2+2 photo addition from two different olefins, so quite efficiently in our case. When the product was less strongly bound to the cavities, then we observed the catalytic turnover. So in this Kuehne-Nagel reactions, even in the presence of 1 mole% on the case, we got the condensed product in a quantity very high yield under almost neutral conditions. In this example, physical properties can be switched. Here is an overcrowded olefin. Due to the static demand of the aromatic substituents, so this molecule cannot adapt planar, so perfectly planar conformation. And the most stable conformation is the unfolded conformation, like this way. Okay? But when confined in our M6 sulfur case, then to fit the symmetry of the case, then this molecule turned, conformation turned into the metastable twisted conformation, because the openings of the cages are so that this way and this way. The two aromatic parts can be also worn out. Then the molecule was twisted into the metastable twisted conformation. The very dark purple color is due to the B radical nature of the two p orbitals twisted deeper double bond. Okay, because of the twisting of the double bond, now the overlapping of the two p orbitals are not very efficient, showing the B radical nature. So that's the reason why it showed so deep purple. We quietly extracted. So we could isolate this metastable conformation. So because the barrier is coming back to the original conformation but high. Based on the same principle, the planar aromatic amide was twisted in our case. When this gas was accommodated in our case, then the amide functional group was twisted by 30 to 34 degrees. Again, the conjugation between a nitrogen lone pair and the carbonyl p orbitals became less efficient. So then carbonyl reactivity is enhanced. So it's closer to the common ketone, common carbonyl compounds. So by twisting, the amide functional group is activated, and the alkaline hydrolysis reaction occurred much faster in our case. For this substrate, we observed the acceleration of as much as the 14 times. So the faster. So again, we did not activate. We did not use the acid or acid to activate the reaction substrate. Only by twisting the molecules, amide functional groups, we could enhance the reaction activities toward a nucleophilic attack of sodium hydroxide. In this case, okay, so when the NBS was it's acted on the triple bond of this bis allyl acetylene compound, then so as the textbook says, the brominium intermediate is supposed to originally form, and the subsequent nucleophilic attack of the aromatic ring normally occurs at this position, also to methoxy group, leading to the anthracene compound. This is a normal product. Okay? But in our case, surprisingly, we obtained quite unusual spiromolecules, so which was formed by the nucleophilic attack of their ipso carbon here. So then we compared the molecular structure before and after the reaction by X-ray crystallography. And we realized that this substrate was pre-oriented so that the reaction center, so this ipso carbon, is very close to the triple bond. Namely, this product light conformation in the case led to the quite unusual formation of the spiromolecule. This is also one of the excellent examples of the molecular confinement effects. So linear molecules are folded. Okay? So in this case, two olefin parts were shielded by the cage, but only the terminal double bond was exposed outside, and the electrophilic epoxidation occurred only at the terminal double bond. Here, these flexible molecules were just confined and folded in this orientation. And we observed efficient tandem 2+2+2 aromatization, leading to the aesthetically hindered B-allyl compound. So yield was so efficient. Good. So in this case, only the in-plane double bond was involved in the aromatization. And this double bond is out of plane or orthogonal with respect to the forming six-membered ring. Therefore, it cannot participate in the reaction. And the only one product, this one, was selectively obtained. So we could modify the nature of the cage itself by attaching the functional moiety on the metal corners. In this case, we observed the visible light absorbing the metal unit. So this complex shows the yellow color and can absorb the visible light. Then in this case, again, we observed the highly efficient 2+2 photodimerization under the irradiation of visible light only for 15 minutes, or even under the sunshine. So we got this product. So DFT calculation showed that the LUMO or SOMO of the excited state is delocalized over the from the reaction center to the a triazine core ligand. So the most plausible mechanism is the energy transfer from the photoreaction center to the ligand and subsequently to the substrate, which is in close contact to the triazine ligand. Anyway, now our case is visible light responsive. We can utilize the visible light for promoting the chemical reactions in the case. So these tripotent ligands can efficiently cap the portals of the triangular the window of the cases, enhancing the guest binding properties much higher. So guest binding properties in the cage was enhanced by capping the windows portals with their trivalent anions. So regarding this phosphine oxide trivalent tripotent capping ligand, then here is an additional metal coordination site. And we could trap an additional metal at the portal of the cage while leaving the large void space in the cage where gas molecules can be accommodated. So now we are very close to the enzyme reaction site, reaction pocket. We are expecting to develop the enzyme mimic reactions within our cage. So size does matter in host gas chemistry. What I mean is, so with increasing cavity sizes, then our chemistry totally changes. So the target species can change from metal ions to small molecules. Then now there are multiple number of small molecules, which we have been showing. Okay? The field has been developed, starting from Crown ether chemistry, then to macrocyclic chemistry, host gas chemistry, molecular recognition. And now, so we can propose molecular confinement. This is a new concept, just above the simple molecular recognition. And quite recently, we could further expand their cavities. And now the target molecule changed to the medium-sized molecules with their molecular weight of around 1,000, which are currently of special pharmaceutical interest. So pharmaceutical companies are very much interested in treating their medium-sized molecules. Now we can target such class of compounds. So our expanded cage was easily obtained by expanding the cage, M6L4 cage, with the aid of the big template molecules. The pyridine was one of the most efficient template molecule to expand their cavity size. So M6L4 stoichiometry expanded into M9L6, but their components are the same. Only the cavity size was expanded 3 times larger than the original one. So we can confine much larger, so multiple number of molecules. Here, so in NMR, around 10 gas molecules, so trimethylbenzene were interacted. So in the crystal structure analysis, we could still confirm 6 gas molecules are well trapped in the cage. So regarding the Calix-Arene, the macrocycles, the 3 macrocycles are well confined in our cage. And the Calix-8 arene is just a flexible molecule. Unfortunately, it doesn't show any specific host properties because its conformation is too flexible. So, but within our case, namely in this host structure, then a Calix 8 array adopted a specific orientation in which efficient guest binding pocket is created. And as expected, this specific conformation of Calix 8 array trapped their guest molecules inside this guest binding pocket. So we could empower their classical host molecules. So these are pharmaceutical molecules, rifamycin and salinomycin, whose molecular weights are over 700. So no host gas chemistry had existed to capture such big, medium-sized molecules. But we can firmly confine these medium-sized molecules, and their conformations are fixed. Then after crystallization, we could easily get the crystal structure of these medium-sized molecules by X-ray crystallographic analysis. So fideoxomycin has the molecular weight of over 1,000, but still it can be well confined. We are now developing the host gas chemistry of medium-sized molecules. This is totally unexplored areas in the previous host gas chemistry. Even the common transition metal complexes can be completely fully encapsulated in expanded M9L6 case. And we have, as a preliminary result, we have confirmed that their catalytic properties changes. So we observed the different selectivities in the reactions with the confined metal complexes in our case. Again, let me emphasize that size does matter in host gas chemistry. So now we have the expanded cavity with the volume of over 1,000 square angstrom. And as I showed at the beginning of lecture, we have much larger case whose interior volume is over 10,000. So we targeted to encapsulate proteins. Again, this is totally unexplored for research area. So we envisioned to fully encapsulate the proteins in a well-defined host framework. Before discussing the protein encapsulation, I would like to show you some our efforts on the self-assembly of molecular spheres. Our first report on the M12 L24 sphere was in 2004. So as I showed in the animation at the beginning of my talk, this spherical entity is assembled from 12 palladium and 24 breaching ligand. Its shape is roughly spherical, but it has the symmetry of a cube octahedron, which is one of the 13 Archimedean solids. So consisting of so combined by the regular polygons, the triangle and the square, triangle and square, like this way. And among the 13 Archimedean solids, so 4 of them have trivalent structures, in which tetravalent structures. So in which 4 edges meet at every vortex. So we are using the square planar palladium. So then a palladium can induce these tetravalent Archimedean solids. Then again we targeted all the structures. Again, so this target can be just a crazy target, okay, from scratch. But we believe that they are brothers, and only by changing their one parameters, namely the angle of their ligands, then we could jump to these larger structures. Actually, so in 2010, we achieved the self-assembly of 2448 rhombicube octahedron, and in 2016, we got the icosydodecahedron. So there are mathematical constraints. Okay, what I mean is we can make the analog change in the self-assembly parameters, mainly the angle of the ligand, but the output is digital, and this analog digital relationship is very important. At a certain range of self-assembly parameters, we can always reach to only one possible structure, so no other structures. And thanks to the mathematical constraint, so restrictions, we could relatively easily jump to these larger structures. Here is an X-ray evidence for the self-assembly of 2448 rhombicube octahedron. You can count 24 metal centers and 48 bridging ligands, forming the square and the triangular width. This is the crystal structure of M30L60 icosydodecahedron. This is a molecular weight, and this is a chemical formula. So, but there is no errors in chemical formula or molecular weight. Now, of course, in the dimension of the molecule. Still, this is a molecule, so not a polymer, with some distributions in the structure and molecular weight and formula. So non-dispersed structure should give us non-dispersed functions. That's the reason why I insist to synthesize the well-defined discrete structure by self-assembly. During our efforts, we encountered a bit curious structure, which was not expected. So unexpected non-Archimedean solids. So here you can see the crystal structure of the M30L60. But this structure does not belong to the Archimedean solids. So it's highly symmetric and roughly spherical, and consisting of only triangle and square. But it does not belong to the Archimedean solids. And more surprisingly, this connectivity has never been discussed in any textbook. So we wondered, what is this guy? So we are a bit frustrated because we have the molecule, we have the X-ray structure, but we could not publish because we could not explain what is this guy. So after careful consideration, and also after the discussion with mathematicians, then finally we could define, which we termed extended Goldberg polyhedra. So let me explain what's the original Goldberg polyhedra. So these are polyhedra made from only hexagon and pentagon. So only from a hexagon, then we get the infinite honeycomb sheet. Okay? So you can imagine the honeycomb sheet, and we can never close the honeycomb sheet. But by incorporating the pentagons, so then we can make the convex surface. And by including the 12 pentagons, we can finally close. The fullerene C60 is one of the Goldberg polyhedra. Well, then the Goldberg polyhedra has the trivalent structure. Just think of the fullerene of a soccer ball. Okay, so 3 edges meet at every vertex. Okay? We simply extended the Goldberg theory from the trivalent to the tetravalent. This is the extended Goldberg. Now the basic sheet structure is just a grid sheet consisting of square, square, square. So tetravalent. So again, we can never cross this grid sheet. But by incorporating triangles, then we can make the convex surface. Finally, we can cross. So, and a series of polyhedra can be generated by simply changing the relative position of the adjacent triangular windows. So, Q number defines the two indexes, h and k, based on this Pythagoras equation. And the h and k defines the relative position of the triangles. So Q number of 5 means h and k should be 1 and 2. So in this structure, from here, 1 step and 2 step, and 1 step and 2 step. Then you can move to the next triangle. And by only changing the relative positions, we can generate. And we so realized that what we obtained was the extended Goldberg polyhedra with a Q number of 5, which we defined by ourselves. So when all the corners, all the metal centers are inscribed in the sphere, then interestingly, the square window cannot be perfectly planar. So one metal corner is slightly deviated from the perfect plane. So strictly speaking, they are not polyhedral. Again, mathematicians say these are not polyhedral because they are not surrounded by the perfect plane. That's the reason why mathematicians had never discussed the series of extended Goldberg polyhedra. But we are against. We don't care such a small deviation. So that's the reason why we encountered so this unusual polyhedron, and so we could develop the new theory that could explain the series of polyhedra so consisting of so square and triangles. Okay, now everything is clear. And but the so this mathematical scientific significance of this mathematical discussion is that so this theory predicted their future structures. Now we have Q number 5 structures, and they are brothers or they are sisters. So why not? Why Q number of 8 or 9 could not be synthesized? Then again, we targeted the next possible structure. Of course, we did considerable trial and errors, but finally we got the Q number of 8 structure. Here is X-ray. So M48 L96 spherical framework was self-assembled from this selenophene quartz ligand. Due to the larger atomic radius of selenium atoms, then this angle became a bit slightly larger. Then that's the reason why we obtained a larger 40, so this structure, which is a tetravalent Goldberg, so extended Goldberg to polyhedron structure with a Q number of 8. So molecular weight is over 47,000. Here is the chemical formula. Probably this is a Guinness Book record or the assembly of giant structure from metal and ligand. Then having such a huge cages, so what game shall we play? Then we envisioned to encapsulate proteins. Now our group is very productive so publishing the many exciting results along this project. Maybe I need another 1 hour talk to discuss everything in detail, but let me emphasize only their conclusion. So most important finding is their proteins are very much stabilized when confined in a discrete cage. So why? Because normally proteins instability is due to the unfolding of the higher ordered structures under high temperature or in organic solvents. Then the protein folding structure is partially broken, and the hydrophobic residue exposed outside. Then they start to aggregate. And this aggregation is, in most cases, the initial step of the protein degradation. However, when the protein molecule is confined in a discrete cage, now they have no opportunities to aggregate each other. Protein aggregation is completely suppressed, so forbidden. So even at higher temperature, or even in an organic rich solvent, protein folding structures are remarkably stable. Okay, so this is the 2D NMR observing the NH correlation of all the amide groups. So the correlations are just mapping on the 2D NMR. So this is just a fingerprint of the protein folding structure. Okay? When we increased the contents of organic solvent until 90%, then finally, so the folding structure was broken, forming the molten globule state, and the enzyme activity was once lost. But when it was rebuffered to the more aqueous conditions, then the original folding structure regenerated. So we observed the chaperoning effect of the cage by only confining the proteins, the damaged protein in the hydrophobic, by the spatial isolation, then the protein folding structure can be regenerated. And we could change the organic solvent content 1% by 1%. And we realized that the unfolding and the refolding process do not occur gradually, but occurs sharply, like a phase transition. So both the protein folding and protein unfolding are phase transition phenomena. And very interestingly, we observed the hysteresis behavior in this way and this way. So we have the example of more than 10 protein encapsulation by changing the size of the cages. In these works, the protein ligands are just covalently anchored within at the interior of the cage. Then normally unobservable weak protein ligand interaction could be observed. So the weak ligand associating interacting ligand is covalently attached in the cage. They are enforced to interact with protein. And by the careful NMR observation, we could specify their interaction regions, so how they are interacting. So here the cartoon shows that the many protein form the stable oligomers. And we would like to see the nature of the interface, but it's hard to observe because the equilibration strongly shifted this way. But in a case, only the monomer could be accommodated because the dimer is too large to be accommodated in the case. Now, in the case, the interface is exposed, and we could easily observe the protein-ligand interaction. Oh, this is a cartoon. A real experiment is shown here. So SOD1 protein dimer was dissociated into monomers within the cage by confining the cage, and its active side, so interface, is now exposed, and we could trap the small ligand molecule. And by saturation transfer experiment by NMR, so we could specify which hydrogens are in close contact to the proteins. Then, and our protein confining cage can be easily crystallized. So unfortunately, we could not see protein. So here, because this is a crystallographic reason. The spherical cage crystallizes into high symmetry space group. And from the X-ray data, from the high symmetry, so the like a cubic space group, then we cannot analyze the asymmetric, low symmetric structure of protein. So unfortunately, we have not reached to the protein structure, but we noticed that this crystal should show their porous nature. So small substrate can easily diffuse into the pore. Namely, we can immobilize the proteins, any proteins in a crystalline state. So this is just imagination. And so we expected the substrate can be, the protein enzyme catalyst can be immobilized in a solid state crystalline materials. And it worked. So this crystal showed some enzymatic activities. And the most exciting result is, any proteins can be co-crystallized under almost their identical conditions. So when these two different proteins are mixed, then co-crystallization occurred. And the two proteins are just involved in the crystal in a random way. Okay? Then what we can expect is, substrate is first converted into the product one. And within the crystal, we can expect the tandem reaction. So further converting to the product two. So this product does not need to go out to the crystal. And this tandem reaction really worked in this transformation. So, this is the experiment when two independent protein confined crystals are examined. So then in this case, the product one have to once go out and re-enter to the second crystal. But here, the tandem reaction can occur within a single crystal. Then the catalytic activity of the tandem reaction was significantly enhanced. Okay, so let me summarize the first lecture. So again, we are developing the cavity. So from starting from square, the cage, and the larger cage, and the giant cages, and depending on the cavity size, we are creating the new fields in host-based chemistry. So, in the second lecture, we'll disclose our infinite chemistry. So if you're interested, you are also invited. Okay, so my today's lecture discloses most of the projects which we have done in the last 3 decades. Too many students, too many coworkers have collaborate with us. We cannot introduce all of them. So the current my students are the representative. Hiroki Takecha is so associate professor in my group. So mainly promoting the molecular confinement effect. And we have more people. So Mitsasukun is dealing with protein, okay, and Sota Sato is responsible for the crystallographic works. So I also thank all the people in my group. Thank you for your kind attention.
Thank you, Prof. Fujita. Will we invite you as well as Prof. Liu to take your seats on stage for the question and answer session? If you have a question for Prof. Fujita, please raise your hand and wait for the microphone. Once the moderator acknowledges you, an usher will bring you the microphone so everyone can hear your question clearly. The floor is now yours, Prof. Liu.
Yeah, wonderful talk. Also very inspirational. I think the student here probably, it's not just a fundamental synthetic organic, inorganic chemistry, but also it's we learned the journey, how you started this research field, and then expanded to many different research directions, including the protein crystallization. We can take some questions from the audience. Yes.
Thank you very much. I have 2 questions. The first question is about molecular design, because you're probably the first one to start this field, right? So I was really curious, when you have those very complex, multiple turns, right? How do you design the ligand in the first instance so that you can predict that eventually it will self-assemble into a beautiful structure?
Okay,
So that's the first question. The second question is about your protein encapsulation. Is the protein in the presence of the ligand to co-self-assemble, or you have the beautiful structure and then you find a way to infuse certain proteins into the pores? Yeah, thank you.
Yeah, so our molecular, actually, this is really the chemistry. So all the structures are designed roughly 50% by based on logic design, but 50% by serendipity. we have to be lucky or something. We need let's think of the 2 extreme. One is just computational or combinatorial chemistry. So trying any possibilities without any logic. Then if you do the combinatorial chemistry with your hands, then you need very, very hard work. Okay, but no logic. On the other hand, let's think of do you know the DNA origami technique? So by designing a sequence, the DNA sequence, then you can exactly predict the resulting structure. Now, so you don't need only the logic. And now it's the DNA origami technique is developed in the field of informatics, because how to make their software is the most important. Okay? But this advantage of the DNA origami technique is you cannot get any structures beyond your expectation. So in our cases, okay, so roughly 50% or more than 50%, we can get their expected structure. So after trial and error, and in many cases we just fail. Okay, but in 10% or even less than 10%, we can get beyond our expected. So this is the most fantastic aspects of chemistry. So we cannot. So our systems are not very predictable, but we can roughly predict. and sometimes we can get as expected. Sometimes, many occasions, we fail, but sometimes we can get the structure beyond our expectation. So that's very interesting. That interesting journey. Then the second question is protein. Actually, there are no host-guest interaction between the protein and the cage, and there is one covalent bond formation, shift-based formation at the so inside of the ligand. So aldehyde formyl group is anchoring, okay, and the N-terminal free amino group forms the shift-base. Then the protein is just hanging to the ligand. Then around the protein, then so the other parts assemble. Then the protein is probably a kind of template. But the initial step is a shift-base formation, covalent shift-base formation, followed by a generation. Then so we can change the cage size. Then we can confine even the small protein to the medium-sized proteins. You can confine the proteins within the polymers, but for wrapping the proteins, then the cationic polymer is necessary for wrapping the anion surfaced protein, or vice versa. But in our case, both the cationic or anionic surface proteins could be confined. And we did not see any significant change in their properties. So
you're using the protein as a template to make a supermolecular structure.
So at the moment, we are not quite sure. So because there are no strong host-guest interaction between the protein, so it still has some flexibility, freedom within the case. But so we may consider the templating.
Yeah. Okay. We take a question over there.
Yeah. Thanks for the very nice talk. So at the start, you showed that rings could interlock together. Can your cages interlock together too to form a big group of cage to put all the enzymes closer together? Is this a symmetry that could be done?
So, yes. So even our three-dimensional cage can interlock to each other. And we have some crystal structures of interlocking cages. But so if it polymerizes, and probably we get the gel materials. Okay? So that so it's so honestly out of our research interest. But we have not particularly studied about the gel formation, materials formation by interlocking.
Okay. Any other questions?
I remember you, thank you very much for your wonderful talk. Yeah, I remember you in your one slide, you showed that the organic molecule with a cyclic double bond form a complex with your cage. And within the cage, the molecule is twisted and show dialectical character. Yeah, the molecule with a double bond, then in the cage is twisted.
Oh, yeah.
Yes, then you see
molecules are twisted.
Yes, then maybe show radical character. Yeah, in that complex, did you observe ESR signal?
Oh, yeah. I think we did. Yes. So we observed the triplet state of the B radical.
Oh, it's very interesting.
Yes.
It's like a twist induce the radical character. Yeah. Okay. Then another, just a very general questions. So for all of the organic molecules, I mean, you with your cage form a host and guest complex. like the linear molecule or molecular folding and then undergo reaction within the cage. So I want to know actually what's the major interaction between the linear molecule and the cage. What's the interactions?
So you're discussing the interaction?
Yeah.
Yeah, actually, the major interaction is so first, so the use of the aqueous solution, so in water is very important because even in methanol, the host gas interaction does not work. So the hydrophobic interaction is the most important driving force, and also the use of the triazine core is very important. If the triazine core is replaced with a benzene ring, benzene, then again the molecular recognition gas binding ability significantly drops.
Oh,
Okay, so benzene ring is the electron-rich aromatic system,
yes.
and it's rather repulsive. So with most of the organic molecules, there is a pi electron, so the repulsion.
Repulsion.
The triazine ring is a electron deficient aromatic ring. So
It's like
so electrostatic reasons, they are at least they are so not repulsive.
yeah. Okay. Okay.
It's a very sticky molecules.
Yeah. Thank you.
Maybe I ask you questions. So as you mentioned, there's origami, the origami structures. But you also mentioned you're using peptide as a linker.
Peptide, yes.
Because it's quite a flexible structure. It seems that you normally you make this a supermolecular structure. You need a very rigid ligand or using metals. But for the peptide-based linkers, I see you can also make a very geometrical structures.
Just if we consider the short fragment, peptide is a flexible molecule. But what we expected was just a folding. After folding, peptide becomes rigid. So
that's repulsive.
yes, yes.
The reaction yield is pretty high, or
Sure.
Okay, we can take a few more questions. I think any questions, not only just the chemistry questions, or anything you're interested. Yeah.
Not mathematical question.
The last part is very interesting. Yeah.
So always very beautiful lecture. So I have two questions. First is a technical one. You make this polyhedron by slightly change the ligand. Sometimes fluorine, then sometimes use ethylene dioxide. So just slightly change. So you make it, your product significantly change. So I answer the angle is important. So any other important factors?
So other important factor is the flexibility of the molecule. The molecule is much more flexible, even the rigid framework.
Yeah.
So acetylene or aromatic ring, their molecules are much more flexible than we think. And when the arm is longer, then this angle can be smaller than expected.
So that means they use some rigidity, right?
Yes. And also the planarity, okay? With the some reagent and substituents, then so aromatic rings can be just twisted this way. Then it cannot form the polyhedral structure.
Okay. Second question, your system is always based on the metal, based on the correlation, can see. So I think chemists are also interested in this like kinetic stable cage, for example. So what are your perspective on that kind of system?
So there are many metals. Some are kinetically inert, and chemically some are kinetically labile. And we at the beginning we examined many metals. So when the metal ligand interaction is too weak, then nothing happens. And also, if the interaction is too strong, then we always obtain the kinetically distributed mixture. So just in between, the metal, the palladium pyrogen interaction was the best.
My question, did you try to convert your correlation system to the kinetically like a covalent bonded system? Not
Okay.
without a metal.
So,
For example, use your cage as a template, and then convert this to kinetically stable covalent system.
okay. So, Yamago-san, the Professor Yamago,
Yes.
so he just converted our
Platinum.
metal directed assembled structure.
Yes.
So via the reductive elimination step.
Yes.
So to the fully covalent system. That's a fantastic example. But this is totally another story. We could not expand to the conversion to the covalent, fully covalent
Okay. Thank you.
covalent system.
Okay. Any other question from the back? Students? If no more question, I think, okay, so we finished today's lecture. But later, if you wanted to take a photo with Professor Fujita, you're welcome to come. Let's thank Professor Fujita for his wonderful talk again. Thank you.
This is Prof. Fujita and Prof. Liu. Our Prof. Xiaogang will present Prof. Fujita with an appreciation of token of appreciation. Thank you, Prof. Fujita and Prof. Liu. Ladies and gentlemen, we've come to the end of this afternoon's session, which we hope has been interesting and insightful. We hope to see you again if you have signed up for part 2 of this lecture series, which is taking place on Wednesday at NTU. Thank you, and we wish you a pleasant week ahead.